Okay, so this is 10th lecture in advanced course in classical logic. And today we discuss Boolean algebras and their representations. In general, a representation means that an abstract structure, an abstract Boolean algebra, is isomorphic to some concrete set theoretic structure in which elements are sets or functions or subsets or relations, and operations are set theoretic operations on these objects, composition or intersection or union, not just an abstract binary operation on them, satisfying some axioms. So on our previous lecture, on some of the previous lectures, we had this definition of a Boolean algebra. So it is a set, non-empty set, containing elements 0 and 1. They are not necessarily different. They may be equal, but then the algebra is called trivial. It is not interesting, of course. We have two binary operations, one unary operation. These we call them conjunction and disjunction, but in theory of Boolean algebras, they sometimes called meet and join. Or supremum and infimum. And this is the complement. And they satisfy quite a long list of axioms, of properties, that are taken from the properties of sets with intersection and union and complement. We know that the classical propositional logic is complete for these structures. A formula is a tautology if and only if it is true in every Boolean algebra. So this is another view on the classical propositional connectives, conjunction and disjunction. Some concrete Boolean algebras, for example, Boolean algebra of all subsets of 3-element set X, Y, Z, can be depicted like this. So we have the minimal, always have the minimal element, which is 0. Here it is an empty set. The maximal and some other sets. Boolean algebras are special cases of lattices. So every Boolean algebra is a lattice, if you know the notion of a lattice. And so here, for example, if we have this element X in brackets and this element X, Z in brackets, then we can take the conjunction. Here it will be empty, and we can take the disjunction. Disjunction, so intuitively means that we take the union. It will be X and Z. But this is a concrete Boolean algebra of some subsets. So in general, if we have some set W, empty or non-empty, it doesn't matter. We can take all subsets with intersection, union, complement, and this will be a Boolean algebra. So a complement of some subset W, A is W, it's a typo, W minus S. So like the complement means the usual set theoretic complement. So these are special examples of Boolean algebras. So are all Boolean algebras have this form? No. There are Boolean algebras of different form, but still they are very close to sets of all subsets. If we take some subsets of W, closed under intersection, union, and complement. So if two sets belong to S, then the intersection belongs to S, union belongs to S, and the complement belongs to S. Then, of course, empty belongs to S because it is X intersection the complement of X. And W, of course, belongs to S. Algebras of this form are usually called a field of sets. So this is a wider family of Boolean algebras. The question is, did we cover all Boolean algebras, all kinds of Boolean algebras? Is every Boolean algebra isomorphic to this one, to a Boolean algebra of this form? The answer is yes. So the general question in the representation theory is every abstract Boolean algebra, so every structure satisfying that long list of axioms, isomorphic to some concrete Boolean algebra. We have two examples of concrete Boolean algebras, so this B is more general. The answer is yes. And the answer differs for finite and infinite Boolean algebras. For finite, we can even prove that every Boolean algebra is isomorphic to a Boolean algebra of all subsets. For arbitrary Boolean algebras, infinite Boolean algebras in particular, they are isomorphic to a Boolean algebra of some subsets, not necessarily to all subsets. Of course, the notion of isomorphism is standard from algebra for any algebras, not only Boolean algebras. We can define what is an isomorphic. This means that we have a bijection that preserves all operations. Well, it is sufficient, of course, to preserve conjunction and the complement, because disjunction is expressible, 0 is expressible, 1 is expressible. So only two operations are sufficient. And so our results today will have two different theorems. Any finite Boolean algebra is isomorphic to a Boolean algebra of some subsets of a set W for some set W. And in particular, every finite Boolean algebra, the number of elements of B will be 2 to the power n for some natural number n. For infinite Boolean algebras, this doesn't hold in general. For example, we already considered this Boolean algebra, the set of all finite or cofinite subsets of natural numbers. It is a Boolean algebra, but it is countable. There is a countable number of finite subsets of natural numbers and a finite subset, a countable number of cofinite subsets. But if we consider a Boolean algebra of all subsets, it always has either a finite number of elements or at least continuum. If W is infinite, so at least countable, 2 to the power W is at least continuum. So this algebra S cannot be isomorphic to 2 to the power n to the power W for any set W. So this is a different kind of Boolean algebras. So let us try to reach this first result. We can say that this is Stone's theorem, but in a very weak form, only for finite Boolean algebras. Stone has proved a similar theorem for arbitrary Boolean algebras, but of course we need some changes here. Okay, so firstly we introduce the inequality in our Boolean algebra. So A is less than or equal to B if the intersection is A. Equivalently, if the union is B, you can easily prove from the axioms of Boolean algebras that these two conditions are equivalent. Or another equivalent condition, not A or B is 1. Notice that this is looks like an implication. So A implies B. Therefore, this less than, so this order behaves like implication. And A and not B is 0. Also, all these four conditions are equivalent. I leave it as an exercise for the listeners. You only need the axioms of Boolean algebras to show the proof is very simple. And moreover, the conjunction and disjunction behave nicely with respect to this order. The conjunction is less than or equal to B, to A and to B, of course. disjunction is bigger than A and bigger than B, and every element is between 0 and 1. So 1 is the maximal element with respect to this order. And again, from the axioms of Boolean algebras, one can easily show that this relation is a partial order, reflexive, transitive, and antisymmetric, but not necessarily linear order, of course. We know that not every two sets are comparable with respect to inclusion. There are sets that such that one is not contained in the other and vice versa. So only partial order. Some remark about notation, about the terminology. If we consider a concrete Boolean algebra of all subsets or of some subsets of W, then this relation turns out to be simply the inclusion. You can easily check that A intersection B is equal to A exactly means that A is the subset of B in the usual sense. And therefore, I will frequently say read A less than or equal to B as follows. A is contained in B, or B contains A, like in sets. But of course, A and B must maybe not sets, but some arbitrary elements of Boolean algebras. But I will use this terminology for simplicity. Okay, so we have a partial order. And with respect to this partial order, some elements may be minimal and some maximal. Let us consider minimal elements. Of course, the minimal, the smallest element in the Boolean algebra is 0. It is not interesting. But above 0, we might have some other minimal elements. So, and they are called atoms. An atom in a Boolean algebra is a minimal non-zero element. In other words, an atom is an element S not equal to 0, such that between 0 and this element, there are no elements. So for any element A, if it is less than, so if it contains, it is contained in S, then it is either 0 or S. We will see later that not every Boolean algebra has an atom at all. We may have a Boolean algebra without atoms. Let us denote at of B the set of all atoms in this Boolean algebra. A Boolean algebra is called atomic. One may think that a Boolean algebra is atomic if it has atoms. No, it is. We give a stronger condition. If it is atomic if every non-empty element, non-zero element, contains an atom. So for element A that is not 0, there is an atom below it, below A. So S is below A. For example, a Boolean algebra with just two elements, 0 and 1, is of course atomic. Its atom is just simply 1. The Boolean algebra of all subsets of X, Y, Z has 3 atoms: singleton X, singleton Y, singleton Z. And moreover, every finite Boolean algebra is atomic. So if we have finitely many elements and they satisfy Boolean axioms, why is it atomic? Let us take any non-empty element. We need to find some atom below A. But if it is an atom, then we are done. If it is not an atom A, then we have some typos here. There is a smaller element So atoms do not have smaller element, but if A is not an atom, it has a smaller element, say B, non-zero element, of course. If B is an atom, then we are done. If B is not an atom, then again there is a non-empty element C that is smaller than B, and so on and so on. So we continue this process, but this process is finite because we live in a finite Boolean algebra here. So eventually we obtain an atom that will be below A. So this is an easy statement. So every finite Boolean algebra is atomic. Some infinite Boolean algebras are atomic too. But some infinite Boolean algebras are not atomic. They even don't have atoms at all. Some Boolean algebras don't have atoms. Okay, one crucial property, important property of atoms. If an atom is below the disjunction, the union, then it is below either the first or the second element. This is a crucial property. So in every Boolean algebra, not only in the atomic Boolean algebra or in finite Boolean algebra, this holds in every Boolean algebra. And this is easier. So if S is below than A or B, by definition, what does it mean? So S intersection of that element A or B equals to S. But here we can rewrite using the distributivity. And now consider this first, S and A. If it is 0, there are two cases. Either it is 0 or it is not a 0 element. If it is 0, then our element S is equal to the second part. And this, by definition, means that S is less than B, as needed. If this is not 0, then notice that this element is smaller than S. But S was an atom. So we have a non-zero element that is smaller or equal, so that is below an atom. Of course, this means that this conjunction is exactly S. It cannot be strictly smaller than S. And this, by definition, means that S is less than or equal. So S is below A. That's it. Okay. Now let us consider not the set of atoms of all Boolean algebra, but for every element, let us consider all atoms that are below this element. So below 1, we have all atoms, but below some fixed element, we have only subset of atoms. It turns out that if we live in a finite Boolean algebra, then this element A can be constructed from these atoms by simply taking the disjunction. In arbitrary Boolean algebra, this doesn't hold. The previous lemma holds for arbitrary Boolean algebras, but here this holds only for finite Boolean algebras. Every element is the sum or union of atoms that live below this A. In fact, for infinite Boolean algebras, we don't even have this big disjunction if this set of atoms is infinite. So there are some algebras in which we cannot define infinite disjunctions. They don't exist. They simply don't exist. But here in finite Boolean algebra, this is okay. It is a finite set of elements. We simply take S1, S2, or Sn. The disjunction of finitely many elements. This is okay. In this lemma, we will use two simple facts. If A is bigger than B and A is bigger than C, then A is bigger than their disjunction. And similarly for conjunction and the inequalities are in other direction. A is less than B, A is less than C, then A is less than B and C. And in fact, we can even prove big more. So here we see that so that B or C, we know that this B or C is bigger than B and bigger than C. And this statement shows that it is the smallest element in the Boolean algebra that is bigger than B and C together. The minimal element that is bigger than B and C. And here, this property shows that B and C, B intersection C, is the biggest element that is smaller than B and smaller than C. Okay. Again, this is an easy exercise from the axioms of Boolean algebras. So let us prove our lemma. We need to prove that A is equal to some big disjunction. Denote this disjunction by B. We need to show that A is equal to B. But of course, A is bigger than every atom below A. And so A is bigger than the disjunction by this property 1. So A is bigger than B is easy. Now let us show the converse. Let us prove that A is smaller than B. A is below B. So by one of the equivalent definitions of this inequality, A and not B is equal to 0. But assume the contrary. Assume that it is not 0. So it is a non-empty element. And our algebra is finite, so it is atomic. So below this non-empty element, there is an atom. So take this atom S. So what do we have? So S is less than the complement of B. S is less than A. But A is less than B. So S is less than B. So the atom S is simultaneously less than B and less than the complement of B. But this is impossible, because then S is less than B and not B, which is 0 by the axioms of Boolean algebra. And so S is simply 0, but this is impossible. An atom, by definition, is a non-empty element. So this contradiction shows that we proved our lemma. And this is the key to the finite stones representation theorem. We can represent every element as a disjunction. So every element corresponds to the set of its atoms. The correspondence is given by this equality. So we are ready to prove the finite stones representation theorem. Stone is a mathematician, Marshall Stone, lived in the 20th century. So we prove that every finite Boolean algebra is isomorphic to 2 to the power W. For some set W, not necessarily non-empty, but in this case, it will be, of course, non-empty. Unless B has no atoms, of course. The Boolean algebra that has no atoms is simply an algebra with one element, 0. 0 equals 1. And we have no atoms, so W is just empty. But in general, this W will be, we take as the set W, the set of all atoms of B. So if B has at least 2 elements, this will be a non-empty. If B has just one element, 0 equals 1, then this is an empty set, and our statement is trivial. One element Boolean algebra is isomorphic to 2 to the power empty. Again, a one element algebra. But in general, let us show that this is what we need. Now we need to define the isomorphism function from b to 2 to the power w. We simply take for every element A, its image is the set of atoms, the set. So at of A is a subset of W. Now we need to show that this is what we need. So this is a bijection, and it preserves, for example, complement and the disjunction. Then it preserves, of course, the conjunction, 0 and 1. So we only need to show this. For the complement. So what happens if we take atoms of A and atoms of not A? It turns out that they are the complement of each other. So we only need to show that the atoms of A and the atoms of not A together cover the set W. So this is a partition of W into two sets. And this is easier. Let us take any element from W. W is a set of atoms. So any atom. Of course, any atom is less than 1. 1 is A or not A. By the main property of atoms, S is below A or S is below not A. So S belongs to atoms of A or S belongs to atoms of not A. So we already have shown that the set W is the union. Why it is the disjoint union? Because, of course, the atom cannot belong to both of them. Because if it belongs to both of them, then S is less than A and not A, which is 0. But we know that atoms are not equal to 0. So this is indeed a disjoint union of two sets. For the union, the proof is even simpler. Why this disjunction corresponds to the union of sets of atoms. Let us start. Take any element from the left hand side. It is an atom. So for any atom S, it belongs to the left part, if and only if this atom S is below A or B. By the crucial property of atoms, it is the same as S or less is below A or S is below B. In our lemma, we said that if this holds, then S is below A or S below B. But of course, the converse trivially holds. If S is below A, then it is below A or B. Okay. And this, by definition, exactly corresponds to S belongs to atoms of A or S belongs to atoms of B. So this or corresponds to this union. So for union, this is trivial. Inductivity. In fact, it is sufficient to show that only the element 0 will be mapped to the 0. 0 in sets is the empty. So if the image of some element is the empty set, then it was a 0 element of a Boolean algebra. Then inductivity follows immediately. We will show this. But let us first prove this simple statement. But this is easier. By contraposition, if A is not 0, our algebra is atomic. So there is an atom below A. So there is an atom in the set atom of A, which is exactly f of A. So f of A is a non-empty set. So this is easy. Now let us prove directly the injectivity. What does it mean, injectivity? If two elements have the same image, then they are the same. If they have the same image, so one set is equal to another set. Then this means that if we take the first set and the complement of the second set, then the intersection is empty, of course. If two sets are equal, then so any set together with its with its complement is of course empty. But then, since F preserves intersection, union, complement, we can rewrite like this. And so we have F of some element is empty. By item 1, we obtain that A intersection not B is 0. And by definition of inequality, we obtain that A is less than B. Similarly, we can show that B is less than A, and so A is equal to B. Of course, in inductivity, conjunction, disjunct, preservation of complement and union and intersection holds for arbitrary case where B is any Boolean algebra. The proof will be different, of course. The construction will be slightly different, but this will hold even in general case. What is specific to finite Boolean algebras is that F will be surjective. It will hold that B is isomorphic to the whole Boolean algebra of all subsets. In general, for infinite case, it will be only an isomorphism to some subsets. So here we will crucially use that our Boolean algebra is finite. Okay, what do we need to show? We need to show that if we take any subset of W, then we will build some element such that F of A is just this element Y. So take any subset of W and simply put, so the set Y is some set of atoms. Let us take the union of these atoms, the disjunction of these atoms. We claim that this is the element that we need. F of A is exactly Y. So this means that for any atom, S is below than A, if and only if S is an element of this set Y. One direction is trivial. If S is an element of Y, so S is one of these elements here in this T, then of course the disjunction is bigger than every element in this disjunction. So A is bigger than every element in this disjunction. So we only need to prove the converse implication. Assume that S is below A. So by definition, this means S is equal to S conjunction A. Now let us calculate in our Boolean algebra. We have that the element S is non-empty. It is equal to S and A. A, by definition, is this big disjunction. And this disjunction is finite because we are in finite Boolean algebra. And now we use the distributivity axiom. Of course, a generalized distributivity because we have many disjuncts here. So we obtain a big disjunction of elements like this. And we know that this disjunction is non-empty. What does it imply? It cannot be the case that every disjunct is empty, because then the big disjunction would be empty. So there must be some non-empty disjunct. There must be some T such that this S and T is not empty. But recall that S and T is below S and below T, and both S and T are atoms. And this conjunction is non-empty, moreover. But atoms cannot have smaller elements which are non-empty. So this S and T must be equal to S and must be equal to T. So S and T are the same. And thus, recall that T was from the set Y. We obtain that S is from the set Y. This completes the finite stones representation theorem. So the crucial was here that we were able to use finite. So every time we rewrite disjunction here, it is finite. And then we use distributivity. In the infinite case, of course, we can sometimes take the infinite disjunction and it exists, it belongs to our Boolean algebra, but we're not guaranteed that the infinite distributivity holds. So this is the problem in the infinite case. Okay. So we cannot, of course, extend this theorem to infinite Boolean algebras for many reasons. Firstly, even for atomic Boolean algebras, we cannot state this theorem. Not for arbitrary Boolean algebras, but even for atomic. So every finite Boolean algebra is atomic. So the next step to generalize is to prove something similar for atomic Boolean algebras. But this is impossible. Because, again, consider the set of all finite and cofinite subsets of natural numbers. This algebra, this Boolean algebra, is atomic. Every set, if it is a non-empty set, contains an atom. For example, it contains a singleton and one element subset. If it is non-empty, it has some element A. So A in brackets is a singleton, is an atom. This atom belongs to S because S has all finite sets. So every non-empty set has an atom below it. But still, we know that this theorem, this algebra, is not isomorphic to 2 to the power W. So the second problem that is that there are algebras without atoms. Moreover, there are countable algebras without atoms. And here is a typical example. The Lindenbaum algebra of the classical propositional logic doesn't have atoms at all. Why did I say that it is a typical example? Because there is a theorem in the theory of Boolean algebras that all countable atomless Boolean algebras are isomorphic. So, in fact, there is only one Boolean algebra without atoms that has countably many elements. And this is the main representative of this class of algebras. So let us recall what is a Lindenbaum algebra. We take the set of all formulas of propositional logic built up from variables using conjunction, disjunction, negation, implication, equivalence, and so on. And we introduce the equivalence on them. Two formulas are equivalent if the equivalence is a tautology. Now we consider the quotient set. It consists of equivalence classes. Then on these classes, we introduce operations and or not. For example, and. If we have two classes, two equivalence classes, then the operation and builds just for the formula A and B and considers its class. We already considered this algebra So this operation is well defined, and it satisfies all the axioms of Boolean algebras, and therefore we obtain a Boolean algebra, an infinite Boolean algebra, moreover a countable Boolean algebra, because if we recall that the set of formulas is countable, so the set of equivalence classes is at most countable, but of course everyone knows an infinite set of pairwise non-equivalent formulas, for example p0, p1, p2, p3, so the variables are not equivalent to each other. So we already have infinitely many and hence countably many equivalence classes. So this is a countable Boolean algebra. As an exercise, please show that it doesn't have atoms. So if you have any element of this algebra, so it is some class A, it cannot be an atom. So assume that it is not empty. It is not, so A is not equivalent to bottom, to false. Then you can easily build a stronger formula. So less than or equal, this relation in this Boolean algebra means that the formula B is stronger than A. And you can easily show that if you have any formula that is not false, that is not equivalent to false, then there is another formula that is stronger, the formula B, such that B implies A is a tautology, and B is again is not equivalent to false. So intuitively, this statement means that there is no strongest tautology. Not tautology, sorry. There is no strongest formula. For any formula that is not equivalent to bottom, there is a stronger formula that is not equivalent to bottom. And this holds not only for classical propositional logic, but for intuitionistic logics, for model, for first order logics, and so on. So this is a very general fact. Okay, nevertheless, Stone succeeded to prove the following remarkable theorem in 1936. Any Boolean algebra is isomorphic to some field of sets. Recall that a field of sets is some subalgebra of the set of all subsets. So S contains only some subsets of W. Well, here we have the notion, the word subalgebra. Of course, the definition of a Boolean subalgebra is standard from algebra. This is simply the subset that on which all operations are defined and which satisfies the same laws, the same axioms, which itself is a Boolean algebra. This is standard. And if we have that one algebra is isomorphic to another algebra, so the first algebra is isomorphic to the second one, and the second one is a subalgebra of a third one, then we say that the first algebra is embeddable into the third one. And now we can reformulate this theorem as follows. Any Boolean algebra is embeddable into some algebra of the form 2 to the power W. So every Boolean algebra is embeddable into some field of sets, into the set of all subsets. Okay, but now how can we prove this? We cannot simply take atoms, because an algebra may have no atoms, and even if it has atoms, it may often be the case that some element A has infinitely many atoms below A. And therefore we cannot take the disjunction. And even if we take the disjunction, even if it exists, we're not guaranteed that this disjunction will be exactly equal to our element A. So there are many problems in the previous proof. So now we need to invent something new. But here, filters and ultrafilters help us. Recall that we already studied filters, but filters over some set I. In our case, it was I. It is a collection of subsets that satisfies these four axioms, four properties. So a filter is closed under superset and intersection. And an ultrafilter over I has additional property that for every set X, either X belongs to phi or its complement belongs to phi. But now we want to introduce the same notion, but for a Boolean algebra instead of the set of all subsets. Therefore, we simply rewrite this definition. Namely, instead of X is a subset of I, we will write that some element is an element of B or of D, it's the same. And we will write A is below B instead of X is a subset of Y. And of course, instead of intersection here, we will use conjunction. And so we obtain the following definition. A filter in a Boolean algebra B is a subset of this Boolean algebra. Notice the subset of a Boolean algebra, not 2 to the power D. Because now D is an analog of 2 to the power I. So a filter will be a subset of D itself. And this filter doesn't have the element 0. It has the element 1. It is closed upwards. If it has some element, then a bigger element is again an element of B, of phi. And it is closed under conjunction from Boolean algebra. And an ultrafilter in a Boolean algebra B additionally satisfies this analog for any element A from D. Either A or not A is an element of phi. And now we can introduce the same notions as we did in the lecture on filters and prove the same results. Namely, for example, we can introduce the notion as some subset of D has the finite intersection property. If we take finitely many elements from E, then the conjunction is non-empty, is not 0. And we prove by the same reason, the same argument, that any set that has the finite intersection property is contained in some filter. And every filter is contained in some ultrafilter. Again, here we will use the axiom of choice. And this, but this statement, this proposition is weaker, strictly weaker. It is not equivalent to the axiom of choice. So in every Boolean algebra, every filter is contained in some ultrafilter. This condition is strictly weaker than the axiom of choice. Okay, so the whole lecture on Boolean on filters and ultrafilters can be rewritten for Boolean algebras. The same properties hold. And now we are ready to formulate the main result. I will only give the sketch of the proof. So every Boolean algebra is isomorphic to some field of sets. To some subalgebra of 2 to the power W. In the previous theorem, we took the set of atoms. Here we cannot do this. Sometimes we don't have atoms at all. But here we will take the set of all ultrafilters. They play the role of atoms in some sense. So we take the set all phi subsets of D that are ultrafilters. Of course, again, we have principal ultrafilters, non-principal ultrafilters. A principal ultrafilter has the form, it contains all elements that are above some atom. The same criterion holds if so a filter is prime if and only if the intersection, or in this case, the conjunction of elements from filter belongs to this filter, and so on. So here we have some ultrafilters are principal, some are non-principal, but this doesn't matter. We take all of them here. As in the previous theorem, let us consider all ultrafilters of A. What does it mean in this case? All ultrafilters such that A is an element of phi. This is an analog of the notion all atoms below A. But this can be defined even if we don't have atoms at all. If we don't have atoms, then here we will have all ultrafilters will be non-principal. Anyway, and then the function is very similar to the previous one. The function from the Boolean algebra B to the set of all subsets, to the set of subsets for any element A from Boolean algebra B, we take all ultrafilters of A. And we again prove that this mapping preserves the complement, preserves the conjunction and disjunction. It is easy to prove for conjunctions here. It doesn't matter. We prove that it is injective, but in general, F is not surjective. We know that not every Boolean algebra has the form 2 to the power W. So simply we don't need to prove that F is surjective in this theorem. And once you know what to prove, you can easily prove as an exercise. Here, this is just some simple tasks to prove these three properties. And this completes the proof of the Stone's representation theorem. So, conclusion from today's lecture. First, we obtained a simpler result that every finite Boolean algebra is isomorphic to the set of all subsets for some W. Every Boolean algebra in general is isomorphic to some subalgebra to the set of some subsets of W for some W. And here we used ultrafilters. S was the set W was the set of ultrafilters. And of course, Stone's theorem was not merely to show that this is a injective homomorphism. Stone proved even more. On the set of all ultrafilters, there is some natural topology, which turns this set into some topological space. It has some special properties known from topology, and this space is called the Stone space. So to every Boolean algebra, we associated some topological space of some special kind. Between algebras, we have homomorphisms. Between topological spaces, there are some continuous mappings. And it turns out that homomorphisms and continuous mappings respect each other. They correspond to each other in a very nice way. So this embedding that we have built in our theorem respects this topology. So if we have homomorphism from one algebra to another algebra, then from algebra A to an algebra B, then it corresponds naturally to some continuous function from the stone space for B to the stone space for A. So in the opposite direction. And if you know something from category theory, then this result can be stated as follows. We have two categories, the category of Boolean algebras. So we have Boolean algebras and homomorphisms between them. And on the other side, we have some specific topological spaces, stone spaces, and continuous mappings between them. So this is the category of stone spaces. And since homomorphisms correspond to the continuous mappings in the opposite direction, then they say this is called the duality between two categories, but in the opposite direction. So this is quite a nice result in the category theory, and one can generalize this to more general objects, Boolean algebras with operators, Kripke frames, algebras for intuitionistic logic, and so on. There are many results of this kind, some deep results that generalize this theorem to other situations. Okay, so this is the end of this lecture, and we can discuss some questions.